Okay, today it's June 29th, and we will be solving daily integrals again. So we're gonna start with the limit again, because this limit is actually very easy. So at first, it doesn't seem like there's much we can do, but when you realize that this is some sort of series, things get much easier. So if you put the n inside, you end up with this series right here, which at a first glance doesn't look like anything, but for one, you can realize that for k equals 0, the value of this series is, the value of the sequence is 0, so this is actually the series starting from 1 to infinity of k times n to the negative k minus 1. The way you solve this is you use a Taylor series expansion, specifically the geometric series, which, if you don't remember, is x to the k from 0 to infinity. And it evaluates to 1 over 1 minus x for absolute values of x less than 1. How is this related to this? Well, if you differentiate both sides of this equation with respect to x, since the series converges absolutely, you can pull the derivative inside of the sum, but you need to make sure that you drop the constant term, because this is 1 plus x squared plus dot dot dot. So 1 is going to be dropped, but the rest of the terms remain, and now we just need to differentiate x to the k. And if we do differentiate x to the k, you get k times x to the k minus 1. Now it's looking a lot more like this. Specifically, this is this series for x equals 1 over n. So our limit of this series can be transformed to the limit of this series, which, well, to the limit of the function the series converges to, which is 1 over 1 minus 1 over n squared, which 1 over n goes to 0 as n goes to infinity, so this just goes to 1. And if we check it out, let's try 1, and 1 is correct. So just use the geometric series to get to this point, and after that it's very easy. Now, I've already done the hard integral, but we're going to start with the beginner integral and go down from there. And I did the hard integral because it's actually a really hard one today, so it's going to take us a while. So let's start with the beginner integral, which is actually of the hardest beginner integrals I've seen. So this is the log base 8 of e to the log base 2 of e to the 1 over x squared e to the 1 over x plus 1 dx. And what you notice is that this is the derivative of e to the 1 over x with a negative. So what we're going to do is we're going to set u equal to this part of the denominator, which is e to the this, okay? Then we differentiate and we get minus 1 over x squared times c to the 1 over x. Then we need to evaluate the bounds of integration. The lower bound is u1 is 1 over 1 log 8 of e, which we can plus 1, which we can write as e to the ln 8 over ln e, which is 1. So this is just 1 over e to the ln 8. So 8 plus 1, which is 9. And the upper bound is, well, 2 plus 1, which is 3. So this just turns into the integral from 9 to 3 of negative 1 over u du, which is ln u evaluated from 3 to 9, which is ln 3. Well, it's ln 9 over 3, which is the same as ln 3. So is that correct? I need to turn this off. ln of 3. Yes. The easy one is actually, I think I'm pretty sure. Okay, technically speaking, it's easier than the beginner one, but you have to have differentiated x to the x before. So x to the x prime is equal to e to the x ln x prime, which evaluates to x to the x times, well, x ln x prime, which is just 1 plus ln x. So this numerator is the derivative, well, part of the derivative of the denominator. So the way we're going to do it is we're going to let u equal x to the x. And then du, of course, is u times 1 plus ln x dx. So du over u is equal to 1 plus ln x dx. And by changing the bound of integration from, it goes from 1 to 2 to from 1 to 4, our integral becomes the integral from 1 to 4 of 1 over u times 1 over u du, which is minus 1 over u evaluated at 1 and 4. So in the end, we get 1 minus a fourth, so 3 over 4. Is that correct? Yes. The medium, again, with the mediums, I don't know what they've been doing with the mediums yesterday and today. These are not medium difficulty, but anyway, so obviously these powers are rather high, so we're not asked to compute these integrals. Or, well, if we are, the trick, there's a very interesting trick that we could do, I guess, but I'm pretty sure we're not asked to calculate these integrals. So first, we're going to realize that the numerator is just the hyperbolic cosine, well, 2 times the hyperbolic cosine of x to the 10th dx, which we can take the 2 outside of the integral, so we end up with 2 to the 10th times the integral from minus ln square root 2 minus 1 to ln square root 2 minus 1 times the inverse hyperbolic cosine, the hyperbolic cosine of x to the 10th dx. Now, the hyperbolic cosine is an even function, so we can extract another 2 here, so we get 2 to the 11th, and then the integral from 0 to ln square root of 2 minus 1 cosine hyperbolic to the 10th x dx. To continue from here, what we're going to do is we're going to let u equals the hyperbolic cosine of x, and then du is the hyperbolic sine of x, but we need to write sine as a function of cosine, which we will use the identity that cos squared minus 1 equals sine squared, and take the roots on both sides. Then we end up with absolute value of hyperbolic sine x is equal to the square root of, well, u squared minus 1. But now we need to remove the absolute values, and the way we do that is, first notice that our integral is on the interval between 0 and ln square root 2 minus 1, but square root 2 minus 1 is less than 1, meaning that ln of square root 2 minus 1 is less than ln 1, which is 0. So this is actually, like, x is always negative here. X is always negative, meaning that the hyperbolic sine of x is also always negative, meaning that this is actually minus that and not plus that. Okay, so finally dx is equal to du over a negative square root of x squared minus 1. And we evaluate the bounds of integration by plugging ln square root 2 minus 1 to cosh. Now, these two are known values of cosh. Cosh of 0 is 1, and cosh of ln square root 2 minus 1 is equal to square root 2. So finally, this integral is negative 2 to the 11th times the integral from 1 to square root 2 of u to the 10th over a square root of u squared minus 1 du. And we could try to evaluate, but I think we've done enough steps to where now we got a 2 to the 11th here, and if we can probably transform the other integral into something that looks like this, we are probably going to be in a good place. So we first take the 2 to the 11th out, and then we do a trig sub, and we let u equal the cosecant of x. Then du is negative cosecant x cotangent x dx. Cotangent of x can be written using the identity that cosecant squared plus 1 equals cotangent squared plus 1. We can write u squared minus 1 as cotangent squared, and since cotangent squared is positive on the interval pi over 4 to pi over 2, this can just be written as the square root of u squared minus 1 equal cotangent t. So in the end, we get that dx is equal to negative 1 over u square root of u squared minus 1 du. And by evaluating at the bounds of integration, cosecant of pi over 4 is square root of 2, cosecant of pi over 2 is 1, but we have a negative, so this is going to flip this from 1 to square root of 2. We're going to have u to the 11th over u square root of u squared minus 1 du. The u's are going to cancel, and we end up with 2 to the 11th times the integral from 1 to square root of 2 of u to the 10th over square root of u squared minus 1 du, which, if you notice, is the exact same integral we had here, except without the minus, so the ratio is going to be negative 1. Good. And let's move on to the hard one, and the hard one was seriously hard, okay? So I'm gonna need a bunch of space for this. So this is the hard one, and it needs a lot of things. So let's first start by using an identity to merge the difference of the inverse tangent. So there's this identity that the inverse tangent of A minus the inverse tangent of B is equal to, well, the inverse tangent of A minus B over 1 plus AB. So we can then write this as the inverse tangent of 4th root of x plus 1 over x minus 1 minus the 4th root of x minus 1 over x plus 1 all over 1 plus. notice that these two are reciprocal, so this is just 1 dx. Let me move this out of the way. Okay, good. So we now simplify a bit, and now the numerator, what we're going to do is we're going to make a common denominator here. So there's a factor of 1 over 2, and then there's a common denominator which is going to be fourth root of x minus 1 times x plus 1, which, however, we know is just the difference of squares formula. So we can write that as x squared minus 1. And then the numerator, this is going to be the fourth root of x plus 1. And we're going to have to multiply with the fourth root of x plus 1. So this is squared, which is just the square root of x plus 1. So we end up with the square root of x plus 1, well, minus the square root of x minus 1 dx. Now, this next step is a very interesting one. There's another interesting identity that the inverse tangent of x is equal to the inverse cosine of the square root of 1 over 1 plus x squared. And this is what we're going to have to do here. Yes, we will have to square the thing inside this bracket. So let's do it. And yes, this is a very grinding integral. You get the square root of 1 over 1 plus. Now 1 over 2 squared is 1 over 4. And we're going to have a factor of square root of 1 minus of x squared minus 1 here, because we're going to square the fourth root. And then we're going to have to raise the numerator to the power of 2, which will be x plus 1 plus x minus 1 minus 2 times the square root of x squared minus 1, because they will multiply. The plus ones go away, and there's a 2x here minus 2 square root of x squared minus 1. So if we write this again, the 1 over 2's can disappear and make the 1 over 4 a 1 over 2. You get a square root of x squared minus 1, and we multiply this by x minus square root of x squared minus 1 dx. What we then do is, 1 over this. What we then do is we make a common denominator on the denominator, or you could also say you multiply the numerator and the denominator by 2 times square root of x squared minus 1, and you get 2 square root of x squared minus 1 plus x minus square root of x squared minus 1 dx. And finally, you can write this as just x plus square root of x squared minus 1. Now again, this doesn't look very friendly, but what we're going to do is we're going to use another inverse trig identity, that the inverse cosine of x is equal to the inverse sine of square root of 1 minus x squared. So then we end up making this identity. After applying this identity, this just becomes 1 minus 2 square root of x squared minus 1 over x plus square root of x squared minus 1 dx, which we can then make a common denominator inside the bracket, and you end up with, well, x plus square root of x squared minus 1 minus 2 square root of x squared minus 1. So this is just x minus square root of x squared minus 1 over x plus square root of x squared minus 1 dx. And now we are at an interesting point where you might see this and go, okay, so what's next? Like, we've applied like 3 trig identities at this point, and we still have gotten nowhere. What we're going to do is we're going to do what I like to call the weird substitution. Whenever you see something of this form, you can do a substitution like this. In reality, this is an inverse hyperbolic tangent substitution, but it's way simpler to deal with it this way. So then du is going to be 1 plus x over square root of x squared minus 1 dx. And why is this important? Because then you get u over square root of x squared minus 1 dx, and we have a square root of x, 1 over square root of x squared minus 1 dx. So we end up with du over u is equal to 1 over dx over square root of x squared minus 1. And now we need to write x minus this. So to do that, we need to solve for x here, which means u minus x is square root of x squared minus 1. Squaring both sides, we get u squared plus x squared minus 2u x is equal to x squared minus 1. The x squares are dropped, so now you get u squared plus 1 equals 2ux. So x is u squared plus 1 over 2u. So x minus square root of x squared minus 1, I'm not sure what that is, but we can find what the square root of x squared minus 1 is. It's u minus x, but u is 2u squared minus u squared minus 1 over 2u, which means that this is u squared minus 1 over 2u, and we subtract this from x, thus we get u squared plus 1 minus u squared minus 1 over 2u. No, plus 1. There you go. The u squares are removed, so we end up with 1 over u, which is perfect. So the bounds of integration now go from 1 again to infinity again, which is perfect. So we go from 1 to infinity. This is 1 over u times the inverse sine of 1 over u, which is 1 over u squared, du. Okay, so always be careful when you apply identities, because I forgot that the identity has a square root here. So this is actually the square root of this, which means that this is the square root of that, which then means that after we make the change of variable, we go from now 1 to infinity, 1 over u inverse sine of square root of 1 over u squared du. And since u is positive, this is just the inverse sine of 1 over u over 1 over u. Now we can let t equal to 1 over u, well, du. And then we go the integral from 0 to 1 of the inverse sine of t over t dt. Okay, so the way you continue from here is you do an integration by parts. You differentiate the inverse sine and you integrate 1 over t, which gives you a ln of t. And this will give you 1 over square root of 1 minus t squared. So this is ln of t times the inverse sine of t, evaluated at from 0 to 1, minus the integral from 0 to 1, ln of t over square root of 1 minus t squared dt. Now at 1, this is 0 because ln is 0. At 0, we need to calculate the limit as t goes to 0, ln of t times the inverse sine of t. The way we're going to do that is we're going to let t equal to sine of theta, which basically does an inverse substitution. So we get the limit as theta goes to 0, ln of sine theta times theta, which is a very interesting limit. The way we're going to solve it is using L'Hopital's rule. We differentiate the numerator and the denominator. So we get cosine theta over sine theta all over minus 1 over theta squared, which means this is the limit as theta goes to 0. Theta minus theta cosine theta over sine theta over theta, which is equal to negative 0 times 1 over 1, which is 0. So this whole term is 0. And the second term, we can now do a trig substitution. T equal the sine of theta. We get the integral from 0 to, well, 1, which is pi over 2, ln of sine theta d theta. Notice that a 1 over 1 minus t squared is actually the cosine theta here. Okay, so these two are actually just our d theta. And finally, well, negative this. Finally, we have this integral, which we solved recently, but we can solve it again, but I'm not going to do that. From now on, I'm going to take this integral as a known result. This is just negative pi over 2 times ln 2. So this whole thing evaluates to pi ln 2 over 2. And holy moly, was this a long and annoying integral to work on. But let's check. But I already know that the answer is correct. This is what it evaluates to when you actually plug in the values for pi and ln 2. But holy, was this annoying to deal with. Anyways, that has been it for the integrals today. Hopefully you enjoyed it, and I will see you all next time. See ya.